Okay, class, welcome to part two, negative feedback. Negative feedback part two. This is from chapter 22, okay? So in part one, talked about transient response, largely. In this one, we're going to talk about accuracy. Okay, so what do we mean by accuracy? Well, let's first build a little negative feedback system. So what I'm going to do is I'm going to generate a unit feedback system. In other words, that the strength of the feedback is unity. We have an output y0 there, an input yi here, and then here we have an error. What I mean by accuracy is how close does the steady state value of y0 match yi. Okay, so that's the question. Okay, the way to answer this question is to actually express this in the Laplace domain first. So I'm going to rewrite this. So I'm going to have, let's do this again. So I'm going to have transfer function g of s in the process itself. The output is going to be x of s. The error is going to be e of s. The input is going to be r of s, okay, and then I'm going to have a unit feedback there, okay, and that's the comparator. All right. Now I know what what x looks like for this. It's just r times the transfer function of the feedback loop, which is g of s divided by 1 plus g of s. Okay, so that's the function that describes this block diagram. Now the error term, e of s, is simply x of s, or r of s, sorry, r of s minus x of s. Okay, so this is just the difference between the two. This is one reason why I have a unit feedback here instead of putting, I didn't put a k in here, for example. Otherwise it wouldn't be as clean as that. So I'm just going to remove that. All right, because then the difference, E of S really does reflect the difference between the input and the output. What I'm going to do is I'm going to combine these two. So I end up with getting ES on the left-hand side. I get R of S 1 over 1 plus G of S. Okay, this is the important equation. Okay, so the error, at least in the Laplace domain, is given by the input, whatever our input is, a step, a ramp, or whatever, and then multiplied by this ratio there. All right. Now, how do we get the actual error? Because I actually want the actual error here. The actual error I can get by using the final value theorem on this expression. So the actual steady state error is the limit s goes to 0, s e s, okay? Or in other words, the limit s goes to 0 for SRS 1 plus G of S, okay? Now, in order to evaluate a particular value for EAS, I have to assume an input for R, okay? So what can be R? Well, the simple one is a step input, so we do a unit step input. If that's the case, RS equals 1 over S, okay? I think we agree with that. So inserting this then into this equation here, we get ESS equals the limit S goes to 0. Sorry, that's a missing 0 there. S goes to 0. 1 over S, S1 plus G of S. Okay, obviously these cancel. So I'm left with the limit. Let's take it to the limit, I'm left with 1 over 1 plus G of 0. Okay, that's basically the answer. Now, G of 0 is often given a name because G of 0, you can, although we've got unit, we have unit feedback, it's actually the loop gain. But it's a constant, right? For the particular system we have is a constant and is often designated KP, which stands for the position error constant. Okay, the error position constant. So the steady state error is 1 over 1 plus Kp. Okay, which we have to remember is G of 0. Okay. All right. So what about a little example then? Well, first of all, actually, before we do that, let's say this. What determines E of S is Kp. As Kp goes up, ES goes down. All right. So I can make the input and output match as closely as I want just by, oops, I meant to increase that, just by increasing Kp. But in order to get ES to 0, I would have to increase Kp to infinity. And if you remember the little simulation we did where we had the car, there was always a difference when we used proportional control. There was always a little difference between the desired speed and the set speed. And that is entirely down to this fact here. Okay, and of course I could increase Kp and it will reduce the distance between the set point and the desired speed, but then I could only go so far because it then would start to oscillate and become unstable. So there's a trade-off here between stability. So there's a trade-off between stability and accuracy. Okay, so there's no free lunch, so to speak. Just to give you an example, let's do an example. So let's say that we have a system where G of S, say G of S, let's say you're given the G of S is 30 over S plus 2. Okay, and you're asked to compute the ESS for a unit step input. Okay, so we know that ESS is 1 over Kp, 1 over 1 plus Kp. And I know that Kp equals G of 0. Okay, and then G of 0 is, and it's really a limit, but G of 0, basically this thing goes to 0, so I'm left with 30 over 2, which equals 15. Okay, so ESS equals 1 plus 15, which equals 1/16. So the error is 1/16. Now this error is compared to the input. The input yi was a step input of 1. Okay, so this is 1/16 of an error. With a unit gain, I expect the output would, under ideal conditions, to be 1, but it won't be 1 because there's a little bit of an error, and that's the amount of error, 1/16. Okay. All right. So I can look at. So there's two other things I can do. I can look at now. What can I do? I can look at different inputs. In particular, the ramp, which is a linear ramp. Okay. All right, linear ramp, and the parabolic, which is basically the square. Okay, does that. So I can look at these two inputs. The other thing I can do is I can look at different kinds of systems. So in fact, they categorize 3 kinds of systems: type 0, which is what we've seen already. Okay, so type 0, and the general form of type 0 will be K, and you've seen this general form before, which is K S plus the zeros divided by S plus the poles, okay, however many there may be. So that's a generalized type 0. They also then have 2 other types, which basically amounts to how many 0 poles there are, okay? So 0 poles. So type 1, type 2. So to get 1 0 pole, you have the same expression right? But now you have an S on its own, effectively S plus 0. Then you have S plus P1, etc. So this tells you that there's 1 0 pole, okay? Type 2 is similar, except it has 2 0 poles. So instead of, so I have this, and now I have S plus 0, S plus 0, 2 0 poles, then I have the rest of it. All right. Now you can also think of this, of course, as just KS plus Z1 dot, 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 all over S squared, S plus P1, etc. Okay. And likewise for type 2, you can think of it as S plus Z1 over S, S plus P1, etc. All right, so these are the three types. So we have three types and three inputs. So we'll get a grid, a 3x3 grid. Now you can go through this kind of analysis using using this form here, right? You can go through this using this form here. You can apply the different inputs. So for example, the unit input, of course, unit step was that. A ramp is 1 over S squared, and the parabolic is 1 over S cubed. Okay, so those are the three kinds of inputs. You can apply each of those to each of the types, and each time take S to 0, because remember we have to work out G of S. We have to basically work out, what happens to G of 0. All right. So what you would do is you would apply. So you take the limit, S goes to 0, S times. You'd apply your input here, whatever the input was, this one, or this one, okay? Then divided by 1 over G of S. Then you take both S's to 0, okay? Both S's go to 0. So if you do that, not difficult to do, you will get yourself a table. And the table looks like this. So what I'll do is, let's do this table, shall we? So let's get a straight line there. So I'll have the type here. Okay, type here. And I'll have a step input, ramp, and parabolic. Okay, this will be type 1, type 0, type 1, type 2. So already, what we've already seen is ESS for type 0 is 1 over 1 kp, okay? All right. Now, for a ramp, I imagine you will realize that if you were to take this S to 0 when you computed this limit, okay, when you computed that limit, and of course it's not equals 0, it's 2, 0, right? When you took it to 0, you end up with a 0 in the denominator, and of course, something divided by 0, well, it's essentially infinity. And so for a ramp, we never match. Basically, not 0, infinity. Right. Basically, what it says is that the output can never match an input if the input is a ramp. Likewise, the output can never match an input if the input is parabolic. Now, it's interesting when you add one zero pole, the error for a step becomes 0. Now, the reason for this is that a single 0 is basically equivalent to adding an integrator. Okay, if you look at the textbook, it gives a short proof on why 1 over S within the transfer function is equivalent to an integrator. And as we've seen, integrators are really good at squashing error because they will accumulate the error until there's no error. And if there is ever any error, it'll accumulate. And so for a step function on a type 1, the error is always 0. Likewise, for a parabolic, you can also do the same for a parabolic as well. For a ramp type 1, we end up with 1 over kV, where kV is this is called the velocity. Let me get that right. It's the velocity error constant, if I'm not mistaken. Yep, it's the velocity. So kV is the velocity position constant. Okay. So I'd have to ramp up the integrator to infinity in order to squash the error if I apply a ramp. Okay. And then for a parabolic input, even one integrator can't squash the effect of a parabolic input. For type 2, we essentially have two integrators. You get a 0 here, and then probably not surprising, you get a constant here, 1 over Ka. And Ka is, as you might have guessed, is the acceleration. Oops. Is the acceleration position constant. Okay. All right, so that basically gives you the table of all the combinations of the step inputs and the type. All right. I mean, the take-home message here is basically you need an integrator. If you want to avoid errors, all right, if you want to avoid errors, you need to have some kind of integration. And we saw that as well with the car simulator. The minute we added integral control, the error disappeared. All right. Okay, and that's two-step inputs. And as we've seen here, if we had two integrators, we can even get rid of a ramp, which is quite amazing if you think about it. All right, so okay, so that's the bit on accuracy. All right, there's a bunch of problems in the textbook which you can go through. All right. The next thing I want to mention in this part is just the linearization. Okay, linearization. So if you have an amplifier, okay, an amplifier with an input and an output amp, right? The perfect amplifier takes the input, multiplies it by some scaling factor, and gives you the output. And this scaling factor is a constant, hopefully at all frequencies. In the ideal amplifier, it would be constant in all frequencies. So if this is an audio amplifier, you get perfect sound fidelity between the output and the input without any distortion whatsoever at all frequencies. Now, of course, there's no such thing as a perfect amplifier, but you can idealize it. You can try and push the bandwidth of the amplifier as much as possible, and you can reduce the distortions as much as possible. And the way we reduce distortions is simply by increasing the loop gain. So if we go back to our feedback, what shall I? Yeah, okay, I'll call it A. And then we have Y out, and then we have a gain now. We have a non-unit gain now. K goes to our mixer error and then the Y input. Okay, so that's our classic feedback model. We know that the output is the input times A over 1 plus AK. All right, we did that almost like in the first or second week, I think. This thing here is the all-important loop gain. Okay, the all-important loop gain. Now, if I push the loop gain up and up and up and up, this one effectively disappears, and I end up canceling A. Okay, and so when AK is much, much greater than 0, Y0 approximates to, sorry, I just made a little mistake there. That should be Yi. Okay, Y0 is approximately equal to Yi times 1 over K. All right. And there are more subtle ways of showing the linearity, but this is an easy one to do. As long as K is constant, okay, if K is constant, okay, then it basically behaves like this. And so we have perfect linearity between the output and the input. Right. Now in op amps, so when you have an op amp, so that's the Y input and that's the Y output. In an op amp, what we do is we take part of the I'm going to do a non-inverting one. We take part of the output. And by part, I mean we take it through a resistor, through a pair of resistors connected to ground. Okay, so basically we're dividing the voltage at Y0. We have two resistors here, and then we feed back part of that voltage back into the op amp. The K is determined by the resistor network. Okay, the A is determined by the gain of the op amp itself. So we can use, high precision resistors, which are pretty cheap, much cheaper compared to the op amp. And maybe we can put them on heat sinks and so on, so they don't warm up much. We can make a very stable K this way. All right. And therefore, this is now a good circuit for amplifying audio. Do the same thing with transistor circuits as well. They do the same thing? They add feedback, and the same principle applies. Okay, so I think that's enough for part 1. Sorry, part 2, and I'll load this up and get on with part 3.